Hi, in this video we'll go over the worksheet solutions for this week's section on decision trees. Here's a quick introduction to the setup of the problem. We have a bit of data on sports players shown here, and we're trying to build a classifier that takes as input features for a specific player shown here. These features are, for example, the position the player plays, the name of the player, and the height of the player, and so forth. And the output of the classifier is going to be the sport that the player plays, in this case basketball or football. In this problem, the type of classifier that we'll be building is the decision tree classifier. Recall that a decision tree is basically a set of rules that we need to follow from the root of the tree. We have some input that we want to classify, and so we start at the root, and for each intermediate node that we pass by, we have a feature, and that feature poses for us a question. The branches coming out from that feature corresponds to the different answers to the question. So for example, for this problem, we have a feature called position. And for the position feature, we could have a node that we might get to. And the branches for this position feature is going to be, we're going to have one branch for each of the positions that are possible. So based on the training data, we could have a guard position, we could have a center position, and we could have a kicker position. And so for a given input, the branch that we will take if we get to this node corresponds to which position that input player plays. Now that we've gotten a quick introduction of what a decision tree is, we need to talk about how to build a decision tree. And the main question here is, which feature do we choose to split on? In order for us to talk about building a decision tree, we first need to talk about how to calculate entropy. The first part asks us to give a definition of entropy. Entropy is a measurement of how many bits in expectation you need to communicate an answer to a query, given that you have a prior distribution over how likely the answers are. This term comes from information theory, which is a whole field in itself, and we're really just going to skim the surface here. Okay, so the definition of entropy is a function. We're going to denote that as a capital H. This function is over a distribution. So here we have an arbitrary distribution p of x. We're going to assume that x takes on n different values, x1 to xn, and the corresponding probabilities for each of these values is p1 to pn. So this entropy function is going to be a function over a distribution, p1 to pn, and the quantity we're trying to compute is the expected number of bits that we need to encode this. So to compute the number of bits that a probability, say p of I, needs to encode, let's think about the uniform distribution with probability p of I for each value. If we have a uniform distribution that has a probability p of I for each value, that means that there must be 1 over p I values. Because when you multiply these terms together, you get 1, which is what a distribution needs to sum to. If we have 1 over pi values, that means that the number of bits we need to encode 1 over pi values is going to be roughly log base 2 of 1 over pi. If we're trying to calculate the expected number of bits, that's going to be equal to the sum from I equals 1 to n of, we need the weight, that's going to be the probability p of I, times the quantity we're interested in, so log base 2 of 1 over p of I. Alright, and that's the definition of entropy. Another way to write this is, so you note that log base 2 of 1 over pi, that's just negative log 2 of pi. And so this expression is equal to the summation from I equals 1 to n pi negative pi log 2 pi. Either of these expressions is fine. I tend to like this one a little more, so I'll be using this expression for the rest of the problems. The next part asks us to plot the entropy for different distributions for a binary random variable. So we're going to plot a curve in the two-dimensional grid. The x-axis is going to correspond to the probability that x equals 1. And for simplicity, I'm going to call this little p. So what's the domain for this value? Well, this value can only take on values between 0 and 1, since it's a probability value. The y-axis is going to correspond to the entropy of our distribution. And here, since we only have two values, the value for, say, x equals 0, that's just going to be 1 minus p. And the value for p of x equals 1, that's just p. Let's first think about the edge cases, and let's start off with the case where p equals 0. And that means that 1 minus p equals 1. When p is 0, we would expect that the number of bits we need to communicate is 0. Why is that? Well, when p is 0, we know that x cannot be 1, and so we know that x must be 0 without even hearing the answer, since that's what the prior distribution tells us, and so we don't need to communicate anything. To show that the entropy function also handles this, we have this equation to use. We have two terms in this summation since it's a binary random variable. And so let's use this equation. The first term we want to consider is for x equals 0. That's this value here, which is 1. So we have minus 1 log base 2 of 1. And then the second term we need to consider is for x equals 1. That's p equals 0. So minus 0 log base 2 of 0. Simplifying this, log base 2 of 1, that's 0. So the first term is equal to 0. For the second term, we have 0 times log base 2 of 0. Log base 2 of 0 tends towards minus infinity. So we have 0 times an infinity term. That's pretty strange, right? Well, to solve that, that's something you might remember from calculus called L'Hopital's rule, where basically you see which function is growing faster, and if you use that rule, it turns out that this expression does tend towards 0. So we have 0 minus 0, that's just equal to 0, which is the answer that we expected. And let's plot this point right around here. In the case where p is equal to 1, we have the exact same scenario just flipped around. And so again, the entropy is 0. How about when p is equal to 1/2? In this case, we can use the entropy equation here. So here for x equals 0, we have 1 minus p equals also 1/2. And so we have minus 1/2 log base 2 of 1/2 for x equals 0. And for x equals 1, again, we have minus 1/2 log base 2 of 1/2. Log base 2 of 1/2 is just minus 1. And so here we have 1/2 plus 1/2, which is equal to 1. And let's put that point right here. You can try plotting different points as well. The final curve ends up being roughly something that looks like this. The key point to take away from this curve is that lower entropy means that the distribution is more homogeneous, meaning we are more confident in determining the answer or value that the random variable takes on. Higher entropy, on the contrary, means that the distribution is more heterogeneous and more spread out among the choices. For the third part, we're asked to compute the entropy of two distributions. First is the distribution of the sports label based on the training data. Let's compute this. Based on the data shown up here, sports is a binary random variable, and it can either be basketball or football. There's 4 samples of each. So for sport, the entropy we're trying to compute is over the uniform distribution over 2 values. And this is exactly what we computed up here. So this entropy is equal to 1. We're also asked to compute the entropy of the position feature distribution. So for the position feature, it can take on 3 different values: the guard position, the center position, and the kicker position. For guard, there's 1, 2, 3, 4 samples, so let's put 4 here. For center, there's 1, 2, so 2, and for kicker, there's 1, 2, there's also 2. So the fraction of samples is going to be, there's 8 total samples, so 4 out of 8 for guard, 2 out of 8 for center, and 2 out of 8 for kicker. The entropy we're going to need to calculate is over the distribution 1/2, that's 4 out of 8, 1/4, and 1/4, each for the 2 out of 8. And we're going to need to use this equation again. So there's 3 terms. The first term is minus 1/2 log base 2 of 1/2. The second term is minus 1/4 log base 2 of 1/4. And the third term is minus 1/4 log base 2 of 1/4. Log base 2 of 1/2, that's negative 1. Log base 2 of 1/4, that's negative 2. Log base 2 of 1/4, again, negative 2. And so simplifying this, we get 1/2 plus 1/2 plus another 1/2. That's equal to 3/2. Now that we've seen how to calculate entropy, let's move on to talking more about building decision trees. The most important part of building a decision tree is to choose which feature to split on next. We have a set of features that we can choose from, so how do we know which feature is the most informative? We need to quantify the value of a split, and to do so, we're going to calculate the information gain for splitting on a certain feature. The information gain for splitting on a feature f is measured by the difference of the entropy before the split and the expected entropy after the split. And the distributions that we're going to pass into the entropy functions are going to be the distributions on the class label, in this case the sport label. The expectation after the split goes over all the distributions after the split, and the weight we associate with each distribution is based on the fraction of samples that went down that branch. Let's see this in action, and hopefully with some examples this will be more clear. The first part asks us to compute the information gain of initially splitting on the sport label. So let's first draw out this split. We have sport here. So initially, we have all our training examples to consider. And since we're only interested in the class label, we have 4 basketball examples and 4 football examples. Since the split is over sport, there's 2 different values that sport can take on, so there's 2 branches. One's for basketball, and one's for football. Now, where do these examples go after the split? Well, since this is over the class label itself, all the basketball samples go left, and all the football samples go right. So what's the initial entropy before the split? Well, before the split, the distribution here was uniform over a binary random variable, and so the initial entropy is over the distribution 1/2, 1/2, and we calculated this from the previous problem to be 1. Now we need to calculate the expected entropy after the split. Well, what's the entropy of the left group? That's just the entropy of the distribution 1, 0. And again, from the first problem, we calculated this to be 0. The entropy for the right branch, that's the entropy of the distribution 0, 1. And that's equal to 0 as well. So to calculate the expected entropy after the split, the weight of this distribution, 4 out of the 8 samples went down here. So we have 4 out of 8 times 0. And 4 out of the 8 samples went here, so 4/8 times 0. So this is equal to 0. The information gain for the sport variable then is equal to the entropy before the split, that's 1, minus the expected entropy after the split, that's 0, which is equal to 1. So it doesn't really make sense to split on the class label since that's what we're trying to predict at test time, and so test examples would not have these labels associated with them. So we're going to split on other features. In this part, we're going to compute the information gain for the decision stumps for 3 features: position, name, and college. Alright, so let's start with position. Let's first begin by drawing out the decision stump here. So initially we have our 8 training examples and they're labeled accordingly. The entropy before the split is the entropy on the distribution here. That's the distribution 1/2, 1/2, and we calculated this to be 1. So for this split, position can take on 3 different values. So we're going to have 3 different branches here. The first branch is for the guard position, the second branch is for the center position, and the third branch is for the kicker position. So now we need to figure out which samples go down which branch. For the guard branch, we'll have 3 basketball samples and 1 football samples. So this group looks like this. For the center branch, we'll have 1 basketball sample and 1 football sample. And for the kicker branch, we'll have 2 football samples. Now we need to calculate the entropy for each of these groups. Let's start from the right. For this group, we have the entropy of the distribution 0, 1, and this is equal to 0. For the center branch, we have the entropy of the distribution 1/2, 1/2. Again, this is 1. For this group, we have the entropy of the distribution 3/4, 1/4, and this is equal to minus 3/4 log base 2 of 3/4 minus 1/4 log base 2 of 1/4. And so now we have the entropies for each of these individual groups. We need to calculate the expected entropy, and so we need to weigh them by the fraction of samples. So for this group, there's 4 out of 8 samples, and this is the entropy expression, minus 3/4 log base 2 of 3/4 minus 1/4 log base 2 of 1/4. For this group, we'll have 2 out of 8 samples, and the entropy is 1. And for the last group, we also have 2 out of 8 samples, and the entropy is 0. So if you plug this expression into a calculator, this is equal to roughly 0.66. And so the information gain of the position feature is equal to the entropy before the split, that's 1, minus the expected entropy after the split, that's 0.66, and so we end up with 0.34. Next, we're asked to calculate the information gain of the name feature, and again we have our 8 training examples shown above, and our initial entropy before the split, that's equal to 1. Now we're splitting on name, and so we have many different branches here. In this case, there are 6 different names, so we'll have 6 branches. The first name we have is Michael Jordan, and that's for a basketball sample. The next name we have Vince Carter, there's 2 of them, and so we have 1 basketball sample, 1 football sample down here. Muggsy Bogues, there's 1 basketball sample. Tim Duncan has 1 basketball sample and 1 football sample. Sebastian Janikowski has 1 football sample, and Langston Walker has 1 football sample. So we're going to calculate the entropy for each of these groups. For this group, there's 1 sample, and so this entropy here is 0. Same with this one here. there's one sample here, again 0, and this one 0. For these two samples, the distribution here is uniform, and so the entropy for this group is 1, and for this group is also 1. Now that we have calculated the entropy for these groups, we need to calculate the expected entropy after the split. So this is going to be 1/8 times 0 plus 2/8 times 1 plus 1/8 times 0 plus 2/8 times 1 plus 1/8 times 0 plus 1/8 times 0. And this is equal to 1/2. So the information gain of the name feature is equal to the entropy before the split, that's equal to 1, minus the entropy after the split, that's equal to 1/2, and that's equal to 1/2. Alright, one more of these information gain examples. Now we're interested in the information gain of college. So let's start by doing the same, putting college as our node here. And again, we have 8 training examples. And the initial entropy is 1. For colleges, there are 5 colleges listed here. So we have 5 branches. The first college is North Carolina. And for North Carolina, there's 2 basketball samples. For Wake Forest, there's 1 basketball sample. For Oklahoma, there's 1 basketball sample and 2 football samples. For Florida State and California, each of these has 1 football sample. Now we need to calculate the entropy for these groups. For this group, since they're all basketball, it's completely homogeneous, and so the entropy here is 0. For this group, again, entropy is 0. This group, entropy 0, and this one, entropy is 0. Now for this group here, we need to plug this into the expression of entropy. We have 1/3 of the samples being basketball, so we have 1/3 log base 2 of 1/3. And we have 2/3 of the samples being football, so minus 2/3 log base 2 of 2/3. And we need to calculate the expected entropy after the split, so we need to weigh these by their weights, which is going to be the fraction of samples that are in the group. So here we have 2/8 times 0, plus here 1/8 times 0. This big group here has 3/8 times this expression, minus 1/3 log base 2, 1/3, minus 2/3 log base 2 of 2/3, and then plus 1/8 times 0, plus 1/8 times 0. And so if we work out the math behind this, we really only need to calculate this term here, and this comes out to roughly 0.34. So the information gain of the college feature is equal to 1 minus 0.34, which is equal to 0.66. Alright, so this part still has a few remaining questions. So do any of the decision stumps that we just computed perfectly classify the training data? Well, here the answer is no. And for the decision stumps for position, name, and college, let's go back to them. Each one of these groups has at least 1 branch where there's at least one basketball sample and 1 football sample. So in these branches, we didn't fully classify the training data because there's some ambiguity here. So this one here, this one here, and this one here. Does it make sense to use name as a variable? So here, the answer is also no. And the reasoning is because name is too unique to a person. So using name as a variable will likely cause our classifier to overfit. For the third part, We're asked how we could best cast continuous variables into discrete variables, since decision trees can represent any function of discrete attribute variables. To discretize a continuous range, we can use any standard binning approach. And through binning, we can essentially create a finite number of bins that captures all the ranges in the continuous setting. The simplest example of a binning approach is a two-way bin, which essentially is an inequality constraint. For part 4, we're asked if we can figure out a few decision trees that classify the training data correctly. So let's come up with a simple one. Let's look at the age variable. Do you notice anything that's different between the football and basketball players based on the age variable? Well, all the basketball players, they're all older than 34 years old. And all the football players, they're all younger than 34. And so we can create a decision stump over the age feature, where if your age is less than or equal to 34, we'll classify the input as a football player. Otherwise, if it's greater than 34, we'll classify the player as a basketball player. So based on this decision stump, we can classify the two test samples that we have. Let's start with Charlie Ward. Charlie is 41 years old, so he'll take the right branch and we'll label him as a basketball player. Likewise, Julius Peppers. Julius is 32 years old, so he'll be taking the left branch and we'll output him as a football player. For the final part of the problem, we notice that in the test set we have a new position called defensive end that we've never seen in the training set. So what should we do if we reach a position split and don't see a branch that we can take? Well, instead of erroring out, we can just greedily take the most likely branch of the split. That is, the one that leads to the greatest number of items. Though this approach might not be correct if, say, the feature was more related to a minority branch, if we didn't know anything about the feature, it's a reasonable choice to make. Let's move on to the final question on pruning decision trees. Here we're given a dataset of two classes, marked with X's and dots. And in this question, we're asked to first see if we can construct a decision tree to separate out the two classes. So does there exist a decision tree that gets this right? Well, let's figure that out. We have to choose one feature to split on first. Let's say F1. And what's a good kind of place to split F1 on? Well, there's something going on where F1 is equal to 0, so let's try that. So let's have the left branch be where F1 is less than 0, and the right branch be where F1 is greater than or equal to 0. So the first split creates something that looks like this. Well, let's consider the left side first. Here we still haven't fully separated the data yet. So if we try to make another split on F2, and again, let's try it where F2 is equal to 0, then on the left branch we have F2 less than 0, and on the right branch we have F2 is greater than or equal to 0. Then here, for all the points where F1 is less than 0 and F2 is less than 0, we're in this area here. So we're going to classify these points as a X. And likewise, for F2 greater than or equal to 0, but F1 less than 0, we're in this group here. And so we're going to classify this as a dot. In a similar manner, for the right branch, we have F1 greater than or equal to 0, so we're considering the right side of the split. We split again on F2, and again have the same branches here, F2 less than 0, F2 greater than or equal to 0. For the left branch, we have all the points where F1 is greater than or equal to 0, but F2 is less than 0. So that's this area, so we'll classify this as a dot. And lastly, we have all the points where F1 and F2 are both greater than or equal to 0, so that's this area. We'll classify that as an X. So yes, there does exist a decision tree that can separate out the two classes. As to whether or not we can find this, we need to take a step back and think about the decision tree algorithm. Decision trees are very powerful and can represent a lot of different functions, and so it is very easy for this classifier to overfit on the training data. To combat this, we look at generalization techniques, and one way to generalize the decision tree is to stop growing the tree when we are seeing that the best split yields a low information gain. For this example, no matter whether we chose F1 or F2 to start with, the entropy before the split, since the data is roughly uniform, the entropy before the split is 1. Now after the split, let's say we did the split on F1, we created, again, this line here. After the split, in the left group, it's still roughly uniform between the dots and x's. Same thing goes for the right group. And so the entropy didn't change from before and after, and so the information gain is roughly 0. If we decided to stop growing the tree, then we would have stopped right here, and we wouldn't be able to find this decision tree. For part 2, we're allowed to grow the decision tree all the way. So yes, if we do that, then we'll be able to find this whole tree. So in order to generalize even in this setting, one other approach is to prune the decision tree. So in the pruning approach, we first build the entire decision tree such that each leaf node has a single class, and we don't stop if the best information gain is too low. Rather, after we finish building the tree, we work our way from the bottom up, and we prune any branches along the way that could have been generated randomly. This helps get rid of splits that could have been due to random chance alone and not due to anything meaningful in the data. That's it for this handout. Thanks for watching.